I'm going to show how to use the DC electric motor component, and then we'll show how to use offset angles on gears. First, let's build a joint here between this rotor and an anchor. We'll just use an axial spring. That's the simplest component that will hold a joint together with forces only along the spring. And then we'll place the motor. The motor connects two ends together, a housing end and an output end. So that's connected. Now we put the joint back together. Let's look for a second. The motor, we're going to give 10 volts. It has a few other constants, some electromagnetic things, winding resistance, and a gear ratio. And you can use all of those. The motor then is this gray contact, two rotating parts, or potentially rotating parts, connected by a transmission of torque through the magnetic field. Then we're rotating the load. We're at a frame rate here in the animation of 3 milliseconds per frame. So this is turning considerably faster than it appears to. 3 milliseconds per frame is 6 or 8 times real speed. Let's do a frequency count and find out the RPM. The easiest way is to look at coordinates at the end of the rotor, either X or Y, and then you can see the motor pick up speed and then settle down as the torque and the damping come into equilibrium. We've got about approximately 3 cycles in 0.2 seconds. That comes out to 15 cycles per second, so about 900 RPM. So that's the speed of the motor. If we reverse the voltage, we reverse the direction, just like with many DC motors. We can also look at the current in the motor. We expect to see a large start current, then dropping off as the back EMF rises with rotation rate. There's the current in the motor. Starts off at about 1 ampere in reverse because we applied a negative voltage. And almost all the current dies away. So we're operating the motor in a mostly back EMF dominated regime, which is good for low heating. Now let's attach a gear train. All the equations that describe how the motor works are inside the component properties and can be modified. Put another rotor and another anchor. Make this anchor nice and big like the others. And the rotor, we want to move one of its connectors onto its center of mass. That's easy to do if you know the right properties to look up. The connector A has an X naught and Y naught coordinate that specify where, when the component is not rotated, where that connector is with respect to the center of mass. We set those both equal to 0, then connector A moves on to the center of mass. And that's all there is to that. Now we'll make the joint. So we'll connect this with a simple axial spring to the anchor. And we'll set the spring constant just to 100. Tighter joints solve more slowly. Of course, they look good in final simulations. And now we'll connect a gear train between the two rotors. The gear train again connects to massy bodies. So we use connect. There's the gear train. And to start off with, let me stiffen the shaft of the gear train a little bit. That's what kappa represents, just like it would for a torsional spring. And the gear ratio is 1:1, so we're just going to try to turn these two rotors in synchrony. Put the joints back together. To put the joints back together precisely, you can type in the numbers of the anchors and the rotors. I'm not going to bother to. Approximate is fine for now. Here what we've got is the second rotor has very high damping coefficients. Let's take a look. Damping coefficient for rotation is, pure rotation is what we're looking at because it's rotating about the center of mass. It's 0.1 Newton meters per radian per second. The same, so that vastly overwhelms this tiny inertia that it has. 20 microkilograms per square meter. So the damping coefficients on the other rotor are much lower. And so what's happening in this case, you can see the motor straining. Let's watch it as it restarts here. The motor straining to turn a system that's limited by a lot of damping at the final part on the end of this drive shaft. And it's just the kind of thing that you'll see. But let's change it so that they turn in a more conventional way. But this is part of the nice thing about simulating everything is even when you've got some bugs, you see familiar behavior. So if we whatever component we select last, when we do control select and can select multiple components, the last selected component's properties will show up here in numbers. And if we enter those, we're setting them on all the components. So I just made the damping identical on these two rotors. We'll run again. Now we get more like what we were, what the setup leads you to expect, you'll see. I can also change the offset angle on these guys. And let's do that now. Let's say that I want this second rotor to lead in rotation. First of all, let's set the rotation to the positive direction, counterclockwise. Make this second rotor lead in rotation by pi/2. Now, if I just turn this rotor as I just did, I'm putting a lot of elastic energy into the gear shaft because I haven't unmeshed the gears and rotated them. I've just forced the rotors at opposite ends of the gear shaft into different positions. So I want to set the offset angle of the gear shaft, unmesh the gears, and turn one of them. Break the shaft and rotate it, and then put it back together. So that the head of this gear train is on the left, the tail is on the right. When the head angle is 0, which in fact it is right now, I want to set the tail angle to pi/2, so that I'm not putting the system in a strange state where it would be the most interesting thing going on would be that the gear shaft is strained beyond recognition. So now we'll run again with this quarter cycle offset and rotation between the two ends of the gear train. And if I haven't screwed up, we'll see. There we go. Same system, but with an offset. We can also change the gear ratio, which will force most of the torque to go. Since the damping on both rotors is the same, most of the torque will be used to drive the last rotor, just because it'll be moving faster. All we know from the gear train is the one turns 4 times as fast as the other in steady state. So there we go. And we can check the motor torque again. And you'd think we should see a little more current in steady state, because instead of pure EMF limiting of the rotation rate, we have some torque limiting. But at any rate, let's plot. So this current there now, instead of diving down to a few percent of the inrush, we've got more than 150 milliamps of current in steady state, it looks like. once we wait for steady state. The inrush current for a few tenths of a second is close to an ampere. We don't want to stall this motor because it will heat up. Heating up is not modeled, although that's in fact easy to do. We could model motor temperature, but a quick proxy for that is just look at the startup current. And all right, that's the demo. Thanks for watching.